Hello friends, welcome to the thrust of curiosity. In this video, we are going to study the mechanical frequency at some smaller level, maybe at micro level or nano level. So we can study the mechanical frequency by using cantilever. Cantilever is a machine or a device which is clamped at one end and is free to oscillate or vibrate from the another end. This is also called as cantilever with one node. Node is nothing but the position at which the value of amplitude or the frequency is 0. So here it is one node. So this cantilever can be called as a cantilever with one node. Similarly, there can be a cantilever with two nodes. So both the ends of the cantilevers are clamped so that they cannot move. So this is called two node cantilever, but they can move from its central part. So the central part can be vibrate. So we can call this as a standing wave. So this will form a standing wave. So as we want to study the system with very low dimensions, we have to study MEMS, that is micro electromechanical system cantilever. Generally they are made up of silicon nitride or some kind of polymers. Now what are the applications of this? As we can see at first, as we have seen here, it is micro. It is used to reduce the size of the system or system size or also the cost. So we use this cantilever, MEMS cantilever, in AFM, which is called atomic force microscope. What is done here is we study the surface morphology of a material. Suppose this is the surface. Here we can say that this is very smooth surface, but this is at classical level. At micro level or at nano level, this surface can be a rough surface. So this surface morphology is studied through AFM. So this is the needle which vibrates up and down, to and fro, to get some information about this surface. This scans all over the surface, and not just scans, it scans with the vibration up and down. So it gets current through tunneling. So I have not drawn all the system, I just drawn the needle. So due to the vibrations of this needle, the tunneling current passes through this needle to AFM or detector. That is basically the data is sent to the computer which analyze the data. So at such a small scale level, the distance between this needle and surface must not exceed than 1 nanometer. So at such small scale we need something which is very small, so we can use the MEMS cantilever, that is micro electromechanical system cantilever. Also we can use such cantilevers in biosensors. So as I mentioned earlier, this will reduce our system size and also the cost. In radio frequency resonator and radio frequency filter also we can use this MEMS cantilever. Radio frequency resonator is basically the, we can say also generator, but this is different from generator as this gives maximum frequency in the range. And filter can be used in the radio communication, or we use mobile, which is our device which we use daily, we cannot remove from our life. So it is operated on the radio frequency. So we need radio frequency filter because we need certain amount of or certain range of frequencies. So to get particular frequency we need radio frequency filter. So in that filter we can use this MEMS cantilever. Now in classical mechanics we have two different laws. The first law is well known, Newton's law of motion, that is F is equal to mass into acceleration, Our acceleration can be written as d2x by dt square, which is the second order derivative of the position with respect to time. And another law is Hooke's law of vibration or oscillation. So wherever we are dealing with the vibrations, we use this law. What this says is, when I apply the force on certain system, let us say spring, so the response will be negative to the force. Suppose I have a spring and I released, okay, suppose I have a spring and I pull down, then release the force, then the obvious reaction of the spring will be opposite to the direction of the force. So if I pull, it will get pushed, or if I push, it will get pulled after the releasing of force. So that's why the negative sign is here in the Hooke's law. But we are not going to tell about the direction, we want frequency. I'm going to equate but without this negative sign. So ma is equal to kx. So I will rearrange, I will put this m, or I will divide m on both sides. So I will get acceleration is equal to k by m into this x. If we relate this with the frequency, this is nothing but omega square x. So omega is a resonating frequency, or we can just say frequency here. So from this we can say that omega is nothing but under root k by m, or we can say k by m brackets raised to 1/2. So this is nothing but omega. So I want the dependence of frequency on the length of the cantilever. So the force constant or the spring constant k here is dependent on the length of the cantilever or the vibrator. Similarly, we know mass is nothing but density into volume. So for a material, density will be constant, but as I change the volume, mass will be changing. But volume is nothing but cube of the length. So it has dimension cubic length. So mass is changing as length cube is changing. So if I put in this formula, what I will get is the omega, the resonating frequency, is changing inversely with respect to L, or I can say omega is inversely proportional to the L. Now what we will do is to get that proportionality constant. So here I am just stating that omega is inversely proportional to L, but what is the proportionality constant we will derive now. So for a cantilever with one node, this is the length of the cantilever, and this L, capital L, is nothing but the wavelength of that wave, or you can also type or write lambda, which is usual notation for wavelength, but I have used here L. So for a cantilever, the length is equal to lambda by 4, or I can say that it is vibrating with such a frequency that its wavelength is equal to 4 times its length. Okay, wavelength is nothing but velocity into time, so I have put L is equal to, or lambda equal to, v into t. Similarly for cantilever with two nodes, this is equal to L by 2, or lambda by 2. So I have written the same thing. So I am going to derive for this cantilever with one node, and the same case is with cantilever with two node. So the difference is only of the factor 2. So I will write t from this. So it will be 4 into L divided by v. 4 into L divided by v. Similarly here it is 2L by v. Now I will write omega. Omega is nothing but 2 pi by t, and t is 4L by v for cantilever with one node. So this will give me the resonating frequency is equal to pi v upon 2L for one node cantilever, and similarly for cantilever with two node I will get pi v by L. Okay, so as we have seen how omega is inversely proportional to L, so this is the constant pi v by 2. So this is the constant, but I cannot calculate v every time. So what I will do is, for 1D cantilever I will substitute value of v. It is generally, this is under root of tension by density of the material. So this is tension in the string or cantilever. This is for one dimension, but if I go to three dimension, it will become T is replaced by Y, that is Young's modulus of the material. So V is equal to under root Y by D. D is density, or you can use rho. So now my omega will be equal to pi by 2L into V. I am using this for cantilever with one node. You can similarly calculate with cantilever with the two nodes. So this is the V root Y by D, that is Young's modulus divided by density of material. Now from this we can clearly say that the resonating frequency is dependent not only on the length but also on the material. So if I use the different material, then the frequency is going to change although the length is the same. Or if I am using the same material, the frequency is going to change if I am using different lengths. Now we will demonstrate a experiment. From that demonstration, I want to convince you that frequency is really dependent on the length of the cantilever.
Okay, so this is steel ruler with 30 centimeter. So I need 2 centimeter to hold this. So what I will do is I'm holding this. So this is 28 centimeter to vibrate this cantilever. So I'm vibrating this. So I must apply the same force if I change the length of this cantilever. So let's start with a smaller force. So this is the force. You can see the frequency. Now I am taking the half length of this 28 centimeter, that is I will put it at 14 centimeter. Okay, so this is half of the previous length and I will apply the same force. Okay, so can you see the change in frequency? You might not seen this because this is very small force, small oscillation. I need to apply some higher force, so I will repeat the experiment with the little higher force. So let me apply higher force with 28 centimeter. We cannot measure actual frequency, but we can notice the change in the frequency. So I will apply higher force than previous. So notice this frequency. Okay, so now I will reduce the length the half at 14 centimeter. Okay, here it is 14. Okay. Now I will apply the same force. So can you see the cantilever is moving faster, or it has higher frequency, and it also damps down very quickly because of the frequency is higher. So in this case frequency was low, so the time period to cover the one oscillation is greater. So we can easily see how the cantilever is vibrating. But in this case we cannot see because it is too fast, frequency is too higher. So this proves that the length, if I vary the length of the cantilever, the frequency will also vary.
Now as we have demonstrated and we have seen that this resonating frequency is really dependent on the L. So now I will solve one problem. For a silicon material, I have silicon cantilever. So the Young's modulus for this silicon is nothing but 182 gigapascal. Giga is nothing but 10 raised to 9 pascal, and the density is 2300 kilogram per meter cube. And I want to know what is the resonating frequency at different lengths for 1 centimeter, 1 meter and 1 micron. Micron is 10 raised to minus 6 meter, or we can also say that is micrometer. So I will substitute in this all this value in this equation. So under root y by d I can calculate first, and then I can change the length. So the value of pi into under root this quantity is nothing but 5.6, or you can get 5.58 something into 10 raised to 4, and divided by L I have kept constant, and also I have calculated upon 2. So you can cross check this. The method is to put just all the values. Pi is nothing but 3.142. So when I put value of 1 meter here, I will get 5.6 into 10 raised to 4 hertz, because unit of frequency is hertz or per second. So 10 raised to 3 hertz is nothing but 1 kilohertz. So I have adjusted this so that it will get in I will get this in kilohertz. So this is 56 kilohertz for 1 meter length of the cantilever. If I use 1 centimeter of the length, 1 centimeter is 10 raised to minus 2 meters. So I will get 5.6 into 10 raised to 4 divided by 10 raised to minus 2. So 10 raised to minus 2 will get to numerator, minus 2 will become plus 2, so 4 plus 2 is 6, and 10 raised to 6 hertz will be 1 megahertz. So this is nothing but, this frequency is in megahertz. If I further reduce the size of the cantilever, I have reached here to 1 micron. Now this will be, L will be 10 raised to minus 6, because 1 micron is 10 raised to minus 6 meter. So this will become 4 plus 6 is 10, and I have adjusted to 10 raised to plus 9. So 56 into 10 raised to 9 hertz. So 10 raised to 9 is giga. So 56 gigahertz is the resonating frequency for 1 micron cantilever. So can you imagine how the larger frequency can be achieved using reducing the length? Now if you keep on reducing the length, you will get the maximum frequency. You will increase your frequency of your cantilever, but there is a limit, because you cannot reduce the size of the cantilever beyond atomic size. So you can easily calculate the frequency, the maximum frequency for which the cantilever can work, and it turns out in the order of 10 raised to 13 hertz. The magnitude can vary up because it is dependent on the material, but you can achieve the frequency in the range of 10 raised to 13 hertz. If you like this video, like, share, comment, and do not forget to subscribe if you have not subscribed yet. Thank you for watching. Have a happy learning.